So my name is Anne. I'm going to present our work on debloating software through piecewise compilation and loading. This is collaborative work between me, my advisor, Dr. Prakash, and Dr. Lakian from Air Force Research Lab. So let me start by introducing the problem that we're trying to solve. Programs are bloated. What do I mean by bloated? So let's take a look at a simple example. So if you look at the program on the left, it is a very minimal program, only one function that returns and does nothing else. So in binary, this program contains two instructions. So when you load this program onto the process memory, when you execute this program, the program only requires a small fraction of Libc to execute the program, to handle the entry point and handle the process termination. And yet, when you execute this program, you have to load the entire Libc onto the process memory. And so therefore, you can see there's a huge chunk of Libc is not being used by the program, just sitting there. That is the code bloating problem. And to provide a big picture of how serious and pervasive this code bloating problem is, we conducted an extensive study of how shared libraries, particularly, are being used by over 2,000 programs that we found on a full installation of Ubuntu 16 desktop version. So let's take a look at the most popular shared library, Libc. So we found that the program that imports most of Libc functions is VLC, and it only uses 21% of the glibc functions. So across those 2,000 programs, we found that only 5% of glibc's functions are imported by the program. What about other shared libraries? If we take a look at this table, we listed the most popular shared libraries being, we ranked them by the number of programs that use the shared library. And we found that for the most popular shared library, glibc, the program only uses approximately 25% of the functions in glibc. And if we take a look at the top 15 most popular shared libraries, on average, only 10% of the functions in those shared libraries are used. What about so there is existing dead code elimination optimization performed at different stages statically. For example, at the compilation stage, you have the compiler perform dead code elimination at the function level for the function body. And then at the linking stage, you have an option to perform cross-module dead code elimination. However, we observe that there is information only available to the loader at the later stage, at the linking stage, about the dependencies between the program and the shared libraries, and between the shared libraries that the program uses. So taking advantage of that information, we aim to bring dead code elimination to the later stage to perform aggressive debloating for the program. So that is our approach. So for this approach, we introduce a framework called Piece-wise that perform a whole program. It systematically and automatically detect which part of the code module you're trying to debloat is going to be needed at runtime, and then remove the part that we're not going to need at runtime. So this framework contains two components. The first component is the compiler, which will analyze the source code of the code module, and then it generates a metadata, the dependency graph, and it writes the metadata onto the binary of the code module. And the second component, the piecewise loader, it will read the metadata produced by the compiler, and then use the runtime information that the loader knows, and then determine which part of the code module will not going to be needed at runtime, and then remove that from the code module. And the result code module is contained less code. To sum up, we bridge the information gap between the early stage, the compilation stage, and the later stage, the loading stage. Of course, this approach has challenges. For example, at load time, you have to determine the dependencies between different modules, between the program and the shared libraries, and with shared those shared libraries is going to need another shared libraries. And then you have statically unknown information, such as the symbol binding information, such as for a symbol name, which definition in the code module it will bind to, and then statically unknown dependencies between the code module from the use of code pointers and indirect branches, and handwritten assembly. Handwritten assembly in the program requires additional handling because the compiler chooses not to optimize the handwritten assembly and send it directly to the assembler to lower it down to the binary. And another type of unknown of challenge that introduces dependencies unknown at the static stage is the use of dynamically loaded shared libraries. So these shared libraries are loaded by the program at runtime, so they may use the part of the code module that we have already removed by the loader. So that also requires special handling. So at the higher level, our system works as follows. The first component, the piece-wise compiler, takes the source code of the code module, analyzes it, and then it produces a dependency graph. Then it writes this dependency graph onto the binary for that code module. And then when you execute a program that requires this code module, the piece-wise loader will read this dependency graph. It's written onto an optional section in your ELF file. So the piece-wise loader will read this dependency graph and use the symbol binding information to determine which function in the code module is required by the program, and then what other functions that were required by the program by importing certain functions in the code module. And then it removes the rest of the code that will not, that the program does not need at runtime. So the result is the debloated code module with less code in the code module. The framework does provide backwards compatibility in two ways. So if you have an unmodified loader trying to load a code module compiled by the piecewise loader, it will just ignore the dependency graph because it's written onto an optional ELF section. So it doesn't require to load that section onto the memory. It will ignore the dependency graph and just load the code module as usual. What happens if you have the piecewise loader trying to load a code module that is not compiled by the piecewise compiler? Then it would just detect that there's no existing dependency graph in this code module, and then just go ahead and perform the normal functionality of the unmodified code loader. So let's take a look into the first component of our framework. So for the piecewise compiler, we take the source code of the code module, generate the initial version of the code graph, and there's missing dependencies in this code graph. We will perform code pointer analysis. We implemented several techniques for this stage. We have globalized code pointer scan, localized code pointer scan, and pointer analysis for C program. For C++ program, we use an additional technique, object-sensitive analysis. And then for inline and handwritten assembly code that we discussed earlier that need additional handling, we will modify the loader, modify the compiler to go through them and detect the control flow relationship between the handwritten assembly and the rest of the code module to add the missing dependency onto the code graph. And then from that code graph, we will generate the dependency graph, and this dependency graph will be written onto the binary file. So to give an example of how this, how the piecewise compiler works, this is the piece of code that we extracted from muscle Libc that handles file input and output. So you have two functions on top, fdopen and open memstream. Each function will generate an object of file of type file. And in this file, in this type of file struct type, you have a function pointer called write. And according to the type of the object, the write function pointer will be assigned to an appropriate function pointer to handle the writing according to the file type. So if you have fdopen, it was assigned stdio write, which did a function that handles the writing to regular file. And if you have memstream, then it was assigned mswrite, which will handle writing to the memstream file type. So when you close the file, the function pointed to by the write pointer will be invoked. So this, we will have an indirect branch in the third function, the close file function. So the initial version of the code graph, you can see on the right-hand side, it's missing the targets for the dependency for the indirect branch in close file, which we know that the two possible targets are stdio write and ms write. So the first approach, global scan, we retain all the address taken functions as global, as part of the global dependency. So because all the address taken functions are valid target of the indirect branch. So you can see we add the two functions onto the graph and assign them as global dependency, and they will be retained at all time. For the next technique, pointer analysis, for pointer analysis, we are able to detect two possible targets for the indirect branch in close file are stdio write and ms write, and go ahead and put that in the graph. And for the next, for the final technique, localized scan, so the observation is that we only retain an address taken function if there's at least one function that takes the address of that function. So for example, if you look at the fdopen function, you can see at the stdio write function has its address assigned to the write function pointer. So the address taken function of stdio write happens inside fdopen function. So if you retain fdopen function in the memory, then you will also retain stdio write function in the memory. So we add that information to the graph that we're going to write to the binary. As you can see here, we add that information, and we do the similar thing to the other function, the open memstream function. We add mswrite to open memstream function, so that if you load open memstream, then you have to load mswrite function. So at a later stage, the piecewise loader will read this dependency graph, it does two things. It performs the regular functionality of the loader, and it also debloats the program. So it reads the dependency graph from the binary, preloads all the shared libraries, gather the symbol binding information at load time to determine which functions to keep and which functions to discard. So after that stage, it will go ahead and remove the code from the binary, and the result is the debloated program. So in this example from the right, you can see that the program uses the function C, and C, if you load C, if you see it in the dependency graph down here, if you load C, you will have to load D. And so in the memory, only C and D are retained. The rest of the code will be removed. So what is the relationship between CFI and Piece-wise? So Piece-wise is complementary to CFI in a sense that it reduces the attack surface by removing the unused code from the memory, and it moreover it prevents the attacker from using the removed code even after the compromise happens. So while most CFI solutions does not consider that post-compromise protection. So if we use two of the solutions together, it will provide, it will improve the security impact of your system. For evaluation, we evaluate our framework for compile time overhead, how much of the code can piecewise remove, and what are the security impacts. So for compilation, we compiled, for compile time overhead, we compiled several shared libraries and measured the time difference that it takes to compile these shared libraries. As we can see, point analysis takes the most time to compile the shared libraries, while global scan takes the least time, and localized pointer scan is in the middle. So to show how much of code that piecewise is able to remove, we're comparing the amount of code that piecewise can remove from the code module versus the amount of code that static linking can remove from the code module. Why static linking? Because static linking, the program produced by static linking only contains the code that the program actually requires. And it provides the upper bound for how much of the code you can remove. So as you can see, we apply both of the piecewise and static linking onto several programs. We have the minimal program, we have the coreutils program, and then you have the benchmarks from SPEC CPU 2006. And on average, we perform comparable to the performance of piecewise is comparable to static linking, with the difference of only at most 5%. Like we remove at most 5% less than static linking. Applying piecewise to a real-world program, specifically curl, on average, we were able to remove around 40% of the shared libraries code, all the shared libraries that curl uses. What about the security impacts of debloating? One observable security impact of debloating is gadget reduction for the shared library. So for example, if we apply piecewise for Libc for a variety of programs, and then we observe that after debloating the binaries, we found fewer gadgets in the code module. So on average, as you can see, we were able to remove 72% gadgets from Libc for coreutils programs, and 73% of gadgets from SPEC CPU benchmarks. And when you remove those code, you also remove the bugs found in the code. So if we take a look at the two shared libraries that we're considering here, zlibc and libcurl, among the code that we actually remove, we found that we also removed these posted vulnerabilities along with the program that uses that and the vulnerability type. So once you remove this vulnerability, even if the program is compromised, the attacker cannot use the vulnerability to their advantage. And we released the artifact of the piecewise toolchain. It is a Docker image, and you can find it on our GitHub account. And if you have any questions, you can contact me. And I'm also happy to take questions now.
Great. Questions?
Hi, John Criswell, University of Rochester. Nice work, but one question I have is when you were discussing the security benefits, you mentioned that it removes vulnerabilities, correct? And that doesn't make sense to me because you're removing code that isn't used. So if the code is not reachable in the call graph, then how can it be used to exploit the program?
Interesting question, thank you. So the code we removed is not used, but if the program is compromised, the attacker will be able to use that code because they can't transfer the control flow to the end to remove code. So they can use the gadgets found in the unused code as well. So
correct, but you were also so that part I at least to some degree agree with, right? I think that requires more evaluation, but that's another kettle of fish. What I'm asking about is when you're removing vulnerabilities, so you're removing vulnerable code with buffer overflows or things, right? So the slide that you had with the CVE numbers, right? You're removing code that's not reachable. Therefore, that cannot be used to exploit the program. You're removing code that could be used post-exploit, right? But you're not removing code with exploits because they're not reachable. So it's not clear to me how that actually improves the security of the program.
Okay. If I understand your question right, so the vulnerability can be used to first take control of the program, or it can be used to perform further attack after you compromise, after you've taken control of the program. So we prevent the using of these vulnerabilities even if the compromise has already happened. So some of the vulnerabilities can be used to perform a denial of service attack from the previous slides.
So are you saying that in the CVEs that you remove, that you've removed the code that the attack uses in the CVE?
I'm sorry? Can you repeat that?
Okay, perhaps we should take this offline.
Okay, yeah.
All right, thank you.
Hello, Jens van den Broek, Ghent University. I have two questions. First is about the way Linux works with shared libraries. So, as I understand how it works, it's like when one application needs, for example, Libc, and it's dynamically linked against Libc, and another application is also run on the system that also uses Libc, then Libc is only loaded once in the memory, right?
Yes.
So basically with your technique, Libc needs to be loaded twice because the code that is not used in one application is removed from the loaded Libc in one address space, and other code that is not used in the other application is removed from Libc in the other address space. So Linux cannot share the memory between the two address spaces anymore. So your memory usage will go up per application that you use, right?
So your question is the memory.
The memory usage, because Libc will be loaded twice in parallel. When two applications are run in parallel on a system, then Libc will be loaded twice because other code will be removed from one instance in Libc versus the other.
Okay. That is, there is memory overhead because when you write to the Libc, which is shared across processes, right? You write to some certain pages of Libc for this process. So you have to create a separate copy of that page for the program that you're debloating.
This is only with copy on write. So
yes,
if you write data, but you say that you remove code, and code is read-only, and code is shared between the two processes. Okay, that wasn't entirely clear. And I think it would be, also that's my second question, it's more of a remark, I think. It would be interesting to also map the load time overhead, because I assume that your technique on the one side has a compile time overhead, but on the other side, the dynamic loader will also need some more time to load the application in memory, because it needs to process the dependency graph and stuff. And this will certainly have an impact when many applications are started on one system, I assume. So it would be nice to see a graph of the load time overhead, I think.
Yes, there is load time overhead. We also discussed that in details in the paper, but I can show you some numbers. For load time overhead, we measure for coreutils program, for SPEC CPU program, and for the curl program. So load time, for coreutils, we introduce an additional of 20 milliseconds. For SPEC CPU benchmarks, we introduce an additional of 30 milliseconds, and for curl, it's 10 milliseconds.
And what's the normal load time for coreutils?
The normal load time is less than 1 millisecond.
So it's more than 20 times, almost 40 times as much.
Sorry to interrupt, but in the interest of time, we have to move on, so we should probably take this offline.
Okay. Sorry. Thank you.
Okay.
All right, so let's thank the speaker again.